Here on behalf of the Naval Academy. Our research team was able to make it out. Navy was nice to let them come out. We started this last year, taking a look at MAC address randomization in mobile devices. And we started out by trying to look at what the actual problem set was, why people were interested in it. The problem here is all 802.11 devices have this globally unique MAC address. And it's constantly being beaconed out in every link layer frame. And you can basically see the privacy, tracking, targeting concerns there. So the mobile devices, the operating systems decided to come up with a way with randomizing these MAC addresses, and we're trying to take a look at how effective those are. So a little bit of background. We're the first to do a wide-scale, in-the-wild collection analysis of randomized MAC address. We do a actually detailed breakdown of manufacturer model and operating systems and how they differ between the different types. And then after we identify how we can find cases of randomization in the wild, we take a look at how we can actually break the randomization schemes. So background, when your devices are not connected to a network, you're actively scanning, sending out probe requests with your globally unique MAC address. And you're basically announcing all the time, everywhere you're going, this is my MAC address. So Apple and Android instituted randomization. And now when you scan for access points, your probe requests are using locally assigned randomized MAC addresses. So the idea here is before you actually connect to a network, you have some modicum of privacy. Just some background on the structure of a MAC address. In the first byte, the second least significant bit is this local bit, universal bit. If that bit is flipped, it's used for locally assigned purposes. So our intuition here was that our randomized MAC addresses would have this bit flipped, and that was our original premise and where we started looking at randomization. Some background on our methodology. We had about 2 years of 802.11 collection. It was IRB approved. We had about 600 gigs of data. We only looked at management frames and unencrypted MD&S packets. Next, after we collected everything, the hard part, turns out, was actually identifying that something was randomized, that the actual MAC address represented a randomized address and not just a peer-to-peer or service-based address using that local bit. Once we broke that down and understood how randomization was being used, we could pull apart the actual flaws in the system. So we start out with hundreds of thousands of MAC addresses. What do? First thing we did is weed out everything that didn't have the local bit set. So we have a smaller, about half of our data set was locally assigned. Next, we pull apart all the peer-to-peer and service-based addresses. In the paper, we'll go into more detail on this, but basically things like Nintendo, or using peer-to-peer on your mobile device, or going in hotspot mode. Local bit is set, but it's not doing randomization. So we weeded all those out. Lastly, and what we'll get into as part of the flaws, is we categorize what was left over as iOS or different types of Android or Windows 10 randomization. And we're left with this. As you can see, over half of our data was locally assigned. That doesn't mean half of our data set were devices. A device can have multiple randomized addresses. That's the whole point. Then we broke down that randomized addresses into different bins. We're going to talk about those different bins and how we can have each of those have different flaws. So the first one we look at is Android with the prefix DA-A119. We saw a considerable amount of this. We took a look at the actual config.xml files for Android operating system, and you can see it's hard-coded as a prefix to be used when doing randomization. So right off the bat, we have this way of identifying randomization for Android. We look for that prefix. We can now say this is a randomized MAC address, and we can move that to a specific bin. Furthermore, a large amount of these prefixes have WPS attributes, which give us the manufacturer and model information so we can see what type of devices using Android are actually doing this. Additionally, some attacks are able to be derived from the WPS attributes. So from the WPS attributes, we're able to identify which manufacturers and models. And you'll see there's not much diversity, specifically in the model diversity. We see no Samsung devices, very little Motorola or LG. That's concerning since Android built in the randomization policy, but we're not seeing. So we're going to keep coming back to that diversity issue. Now we have a large subset of DA-A119 prefixes that don't have WPS information. So we don't know what manufacturers and models those belong to. So the granular details of how we figured out these are in the paper, but basically we take MDNS packets that have DNS model information in the DNS.text field. We take the global MAC address from those, find probe requests that have that same global MAC address, and derive a signature of what that probe request looks like. And we'll look at those signatures more later. But using that, we can guess what type of models match that signature when they're using randomized MAC addresses, purchase those devices, and then match them up. So we guessed that those were the devices that we thought they were, that were doing randomization. We bought them, confirmed that the signatures matched, and matched the randomization scheme that we saw. As you'll see, Samsung and Motorola are still absent. Next, we have a prefix for Android, 9268C3. This is actually an OUI that replaces that Google CID. It's owned by Motorola with the local bit set. Turns out that the only device that uses this is the Motorola Nexus 6. It has the attributes that we talked about from WPS to delineate that. However, they don't use that MAC address prefix as their actual MAC address. They have a different OUI owned by Motorola and jump to this hard-coded 9268C3. Again, an easy way to identify randomization, look for that prefix. We're still missing Motorola and Samsung, which is very distressing since Samsung global addresses were 22% of our client-based probe requests. They're just missing. So next we looked at non-standard randomization. Did we find OUIs without the local bit set that made up an oddly high number of occurrences in the data set? From that, we saw that Motorola was keeping their OUI and only randomizing the last 3 bytes of their MAC address for a specific device. Using our previous techniques with MDNS, we purchased the devices that we saw doing that, confirmed that in our lab. Lastly, we never saw Samsung in our data set ever randomizing. In our lab, we couldn't force it to randomize at all. Looking at the actual OS code, it tries to do randomization, but fails. We believe it's a chipset issue based on Samsung's proprietary 802.11 chipsets that somehow break the ability to do randomization. And this might be why we don't see a larger diversity on other models as well. Excuse me. Lastly, we have iOS. So iOS has been doing randomization for a while, since 8.0. And it was very, very difficult to find iOS randomization. They don't use a prefix, so that's out. They don't use WPS, so we couldn't find it that way. So what we first started off was an incredible amount of pre-work deriving device signatures in the lab and matching those up and using that as a way to identify iOS devices. Well, luckily iOS 10 came out. They added an information element in the probe request that said, we're iOS. So that made it really easy for us to bin all those devices as iOS, making it less computationally intensive. Lastly, iOS does something good for them, is they randomize the entire 2 to the 48th minus the local bit and the multicast bit, so it's much more random, obviously. So now that we can actually identify and bin different types of randomization, DA119 with WPS, without WPS, 92683 in iOS, we can take a look at what flaws work against each category to try to de-randomize that MAC address and get the global address back. So first we want to highlight the adoption rate itself is really problematic. Obviously, if a device isn't doing randomization, it's trivial, but more put to the point, if so few devices are randomizing, there's not much noise that you have to look at. You only have to look at the few phones in the audience that are actually doing randomization and try to de-randomize those. If everyone's randomizing, the problem's much harder. Next, and this one was also very disconcerting, is this global probe request while randomizing. So we saw across the board for Android devices, you would be sending out random MAC addresses for your probe requests, and then periodically send your global MAC address and a probe request as well. Well, using our device signatures, we'll talk about more in the paper, using the sequence numbers that are incrementally, monotonically increasing, we can basically link those together. So an active user actually increases the likelihood of global probe requests being sent. Anytime you touch your screen, turn on your screen, get an incoming call, you basically trigger a probe request with your global MAC. Previous research talked about this UUID reversal. It comes from a WPS attribute. The problem here is the UUID is constructed from the actual MAC address with a non-random seed. So you can link your global and non-global probe requests with the UUID, or if you only have the locally assigned one, you can use a pre-computed hash table and derive the global MAC address. What wasn't done in previous work is really highlighting what manufactured models this could work against, whether this actually works against randomized devices and not just anonymized data. So what we did is we put this against our entire data set and saw that only about 30% of devices actually use WPS while randomizing. So there's a large amount left over to try to attack. iOS doesn't use WPS at all, and WPS attributes hopefully will start to go away in general, and this attack won't be as useful. And we did confirm that the MAC address that's used in the computation is the Wi-Fi MAC address and not the Bluetooth address. So this is just a quick overview on the device signatures. Basically takes the information elements of your probe request. So 0 represents the SSID field. If that exists, it goes in our signature. We build those out. And we can use that to weed out all the different devices that aren't similar. So iOS devices look very different from an Android device. An iPhone looks different from an iPad. So we can segment the different devices and addresses we're looking at, clear out the noise. And we'll use this in combination with sequence numbers and the other flaws like the global probe requests to put these all back together. Another method that we can use passively is linking association and authentication frames back to the probe requests using the sequence numbers. They stay monotonically increasing as they transit from a probe request to trying to associate to an access point, but switch to their global MAC address. This one only works if you actually were lucky enough to collect while somebody is trying to associate and authenticate. So this brings up the karma attack that's well known. It's basically an extension of the fact that the global MAC will get sent if you try to associate. So that's not terribly novel, but what we saw that was interesting is with the use of Hotspot 2.0 and EAP SIM, EAP AKA to automatic offloading from a cellular network to the Wi-Fi network, directed probes are being used more and more. That largely went away because of security concerns with the karma attack, but now the mobile providers are hard loading in access points that you will now send directed probes to. So now we can see those again and reinstitute the karma attack. Lastly, we have this control frame attack. So our premise here was if we were lucky enough to know a global MAC of somebody we cared about ahead of time, can we elicit a response from a device while in a non-associated state while randomizing? So we looked at the different states the device could be in. We're concerned with state 1, non-associated, non-authenticated. So we want to look at class 1 frames, frames that you can send to a device or a device can send. So we went through these, and the only one that worked out successfully from us was using RTS-CTS. So what we do is we send a request to send to the device's actual global MAC address. Even when it's randomizing, it will respond. A little tricky here is it doesn't include its MAC address in the response. Those control frames don't have that. So you come up with your own unique address that doesn't exist in the environment. And if it responds to that address, then you know it was there. And we saw this worked across the board for Android and iOS. One caveat is usually iOS will only respond if the screen is on. We consider that a chipset flaw that won't be easily fixed by the operating system. So we did get a lot of calls from Qualcomm to try to work on that. This is an overview of all of the attacks and how they work against the different bins. So just in conclusion, Android devices are just a mess. They're not being universally employing randomization. They use different schemes. They're easily identifiable, and therefore you can apply various implementation attacks. iOS does a lot better job. Passively, it's more difficult to get that global address back unless you get lucky with an association frame. However, when they included that extra field, it made it a lot easier to at least identify that you're looking at an iOS device that's randomizing. So we made a few recommendations. First off, we recommend that the IEEE standardize randomization policies, that it's universally adopted, so that it gets rid of that issue with adoption rate. We would like to see the information elements and probe requests go away, so you can't use device signatures. The byte structure and how you use that should be derived from an IEEE policy. And lastly, we believe you should remove sequence numbers from probe requests because they effectively aren't useful as probe request structure. That concludes my brief. If there's any questions.